In lesson 2.4, we're going to continue working with permutations and counting. We're going to look at something called the rule of sum. We're also going to look at something called an indirect method of counting. So let's get to it. Recall that the rule of sum, or additive principle, is for mutually exclusive events, right? And mutually exclusive events are events that, if you talk about two events, if one occurs, the other one can't. One event excludes the other. So take anything that can't happen at the same time. The Los Angeles Dodgers just won the World Series. So, and they are playing the Tampa Bay Rays at this moment. So either the Dodgers won or the Tampa Bay Rays would win the World Series. Those are mutually exclusive events. They couldn't both win. You name it. Anything that where one choice rules out the other is mutually exclusive. So as far as counting things up goes, if there's m ways of one event occurring and n ways of another occurring, since it can either be one or the other, then there's m plus n ways of one or the other happening. So we got m ways, we got n ways, so one or the other can happen in m plus n ways. So if I could get to, let's see, if I could get to work in 5 different ways, 5 different paths, or I could get to the store, and I can get to the store in, let's say, 7 different ways, then I wanted to know how many ways I could get to either work or to the store. Then there would be 12 ways I could get to work or to the store, because it would be 5 plus 7. Just think of examples. Let's look at a more complicated one, though. At an international conference, either 8 or 9 countries may attend. Okay, that's no problem, 8 or 9, yeah. However, we want to talk about arranging all the flags in a row. Well, now what are we going to do? Because we don't even know if there's 8 or 9 countries coming, so how can we come up with different ways of arranging them all? Well, if we want to arrange 8 flags, say 8 countries come, then you've got 8 flags, and we want to arrange all 8 of them, so it's 8 arrange 8, which is 8 factorial. Or maybe 9 countries come. And again, we want to arrange all 9 of those flags, so it would be 9p9 in that case, or 9 factorial. But these are mutually exclusive. So the part that's mutually exclusive in this example is you can't have 8 countries and 9 countries come. You can't have exactly 8 countries at a conference and exactly 9. If you have 8 countries there, you don't have 9. If you have 9 countries there, you don't have exactly 8. So it's one or the other. So the ways to arrange 8 or 9 countries, since they can't both happen, would be 8 factorial plus 9 factorial. Eight factorial plus 9 factorial equals 403,200. Recall that we have this rule of inclusion and exclusion also for non-mutually exclusive events. And that was the same as the rule of sum, except that we had that overlap we had to subtract, right? If things were not mutually exclusive, then sometimes we have elements that could occur at the same time. And otherwise, if we don't subtract the overlap, we're going to count them twice. So let's look at an example of that. 3 players cut 1 card from a standard deck. If order is important, how many ways could there be all hearts? All right, so the 3 players is our R value. That's how many cards are being chosen. And we assume that they're not putting them back in. They're not returning them to the deck. So R is going to equal 3. So how many ways could there be all hearts? Well, there's 13 hearts in a deck of cards. There's 52 cards altogether. But we don't want all 52. We only want the hearts. There's 13 hearts, which means that n equals 13. That's how many we have to choose from if they're going to be all hearts. And how many ways can they still... There's still many different ways that they could be all hearts. And so if n equals 13, and R, the number they're choosing, is 3, then it's going to be 13p3. Otherwise, it's going to be 13 factorial over 13 minus 3 factorial, which is 10 factorial. Otherwise, it's just going to be 13 times 12 times 11 using the fundamental counting principle. Type it in your calculator how you like. You should always get the same answer of 1,716 ways that you could have 3 different hearts from a standard deck. If we move on, and that's not, that's got nothing to do with mutually exclusive events. There's only one event happening here, and that one event is those 3, that draw of 3 cards. So here's a different event that they're all going to be face cards. So for those of you who play cards, you would know that there's 12 face cards. There's there's Jack, Queen, King of each suit, and there's 4 suits. So 4 times 3 is 12 cards. So n equals 12 in this case. We're still drawing 3 cards, so it's 12, choose 3. Sorry, again, using choose. I shouldn't say that. I should say 12p3, because we're going to see that choose means something different. So it's 12p3, which again, using the formula, would be 12 factorial over 12 minus 3 factorial, which is 9 factorial. Could type that in the calculator, or we could just go, okay, that's 12 times 11 times 10. I don't need to draw the line under it. And again, so those are 3 different ways you could type it into your calculator. But however you do it, I get 1,320. Now, all hearts or face. Now, this question is actually a little bit vague, this part I find. When they say all hearts or face cards, I'm going to interpret this to mean sorry, I was going to write something else, but I'm going to interpret this to mean 3 hearts or 3 face. So they're all hearts, they're all just hearts, or they're all just face. So not a combination, because if you think about it, you could read this another way, think that they're all going to be hearts or face, as in maybe I've got 2 hearts and 1 face that's not hearts, or maybe I've got 2 face cards and a heart that's, the face cards aren't, again, hearts. And I'd have to approach this differently if I interpret it that way. So I'm going to interpret this as, at least, so I could do it both ways, actually. But if I interpret it as all hearts or all face, we've already answered the first part. If it's all hearts, then there's 1,716 ways of doing 3 hearts. And there were 1,320 ways of doing 3 face. We would add those together. However, there's an overlap. These are not mutually exclusive. I'll just write ME for mutually exclusive from now on. But it's not ME. There's 3 overlap, right? There are, let me draw a Venn diagram, in fact. I haven't drawn one of those for a while, so I'm due. So if there's 13 hearts, well, actually, let's work. It's often good to work from the inside out. We know that there's 3 hearts that are face cards. There's the Jack, Queen, King of Hearts. So we got those 3 for overlap. And if there's 13 hearts altogether, then we got the 10 on the outside here. So together, this whole circle, if I add these together, then yeah, I've got 13 hearts. There's 9 face cards that aren't hearts. There's the spades, clubs, and diamonds. So if I add those together, though, I got my 12 face cards. So this Venn diagram shows there's actually 3 cards that are both hearts and face cards. And I don't want to count them twice. So what I can do is I can remove the arrangement of face cards that are hearts. And it's not just 3, because they can be rearranged as well. So these 3, there's 3 face cards that are hearts, and I'm still choosing 3 cards. There's 3 players anyway choosing, so R is also 3. So there's actually going to be 3p3 ways of arranging them, which is 3 factorial. So there's actually 6 ways of choosing face cards and hearts at the same time. 6 ways of arranging the Jack, the Queen, and the King of Hearts. That's the overlap that I have to subtract. When I do that, I get 3,030. So there's 3,030 ways they could be all hearts or all face. That would be a clearer way of writing it, all hearts or all face. But the key for this one is understanding that because they're not mutually exclusive, I absolutely have to subtract the overlap. So as I said, this was a vague way of being worded. Another way that this might be interpreted is what if, again, we could combine hearts with non-heart face cards. In that case, there's 13 hearts plus 12 face cards, but again, 3 of those face cards are hearts, so I have to subtract that. There's actually just 22 cards to choose from. And in that case, I'm thinking of it as one big group. It's not involving the rule of, sorry, I was trying to find it for us here. It's not involving the rule of inclusion and exclusion. It's simply grouping them into one big group and then figuring out how many ways we can pick 3 cards out of that. So in that case, it would be 22. That's our n value. P3. And it's going to be a lot bigger number if we're not making it be all hearts or all face. And again, that would be the same as 22 factorial over 22 minus 3 factorial, which is the same as just 22 times 21 times 20. Again, pick your way of typing it in. But I come up with 9,240. So, 2 different answers depending on how we interpret it. That would only be if it's okay to combine hearts and face. I should say non-heart face. Cards. All right. Then we have the indirect method. So this is another really important concept. This indirect method is going to allow us to count things in a much easier way in certain circumstances. Using the indirect method, what we do is we subtract the number of unwanted outcomes from the total number of outcomes to get what we actually want. If we think about it this way, we're counting things up, right? And at its most basic, we can think about them as the things that we want, the things that we're counting, and everything else. And everything else can be unwanted. So the wanted outcomes plus the unwanted outcomes add up to the total number of outcomes. There's no other option. You either want them or you don't. So they add up to the total number of outcomes. Sometimes it's easier to actually count the unwanted ones and then just subtract them from the total number of outcomes than trying to count all the different ones that we do want. That's the indirect method. We're going to see that in this last example, but not until we get down to part C. So let's get going on it. There's 3 players on a basketball team lining up for the year-end photo. How many arrangements can you make if there's no restrictions? This is like an example we did in the last lesson with 8 books that we're lining up on a shelf. So it doesn't matter if it's people or books or whatever. We've got 8 things. And in this part where there's no restrictions, we're just lining them all up. So R is also equal to 8. So we just want 8p8, which is the same as 8 factorial. 40,320. You may even remember this from the last lesson. Okay, there we go. The captain and the assistant must stand beside each other. That's very similar to an example we saw before as well. So it was like when we had to keep the 3 books together. So we got 8 spots in this photo. The captain and the assistant have to be together. I'm gonna explain it slightly different in this case, though. So let's pretend that the captain and the assistant are on the left. They don't have to be, but let's just start off assuming they're on the left. So we got 2 choices for these 2 spots. Either the captain or the assistant can go in the first spot. Doesn't matter which one, but there's 2 choices. Whichever one I pick, there's only 1 person left to go in the other spot. Then there's the other 6 members of the team, and they can go in any order. So in this spot, I've got 6 choices. But after I place someone, then there's 5. And then there's 4, and 3, and 2, and 1. So these are all multiplied together using the fundamental counting principle. That takes care of everything except for one fact. And that's the fact that I've already talked about, that they don't have to be on the left. So the captain and the assistant, instead of being on the left, maybe this first person's over here, and they're, that this group is second from the left. Or maybe 2 people are to the left of them, or maybe 3, and so on. So I can think of the captain and the assistant as a unit. So think of them, they're together. They have to be, if I move them around anywhere, that's fine, I can do it, but they have to be together. So really think of them as one extra thing. So if this is 6 members of the team that I can arrange, then this is 1 extra unit. So really I've got 7 things that I'm trying to arrange. The 6 regular members plus the captain assistant unit. So I'm arranging 7 objects, which is 7 factorial. And then within those there's 7 objects. I've got this captain and assistant, and they can be in any order. I can arrange those two by 2 factorial. And if I do that, sorry, I just want to delete a couple things. Okay, back to 2 factorial. That will get me the same answer. 7 factorial times 2 factorial, or just 7 factorial times 2 will give me the correct answer. 10,080. Okay, the last example, and this is the one that actually does use the indirect method. The captain and the assistant must not stand beside each other. So, if they cannot stand beside each other, then that opens up a whole can of worms, because maybe there's 1 person between the captain and the assistant, or maybe there's 2, or maybe there's 3, or 4, or 5, or all 6. I can actually calculate all these different combinations, all these different permutations, but it would be a lot of work. I'd have to figure out how many ways can I do it with exactly 1 person between them. And then I'd have to figure out how many ways can I do it with exactly 2 people in between them, and how many ways with exactly 3 people, up to 6 people. And then using the rule of sum, I could add them up. Or I could just take the answer I already have of the number of ways where they are beside each other and subtract it from the total number of ways of arranging 8 people. So I guess I never really talked about the formula here, so let me just come back to it for a second. This is the actual formula. That's a simple enough formula. It says the number of ways of counting wanted outcomes is equal to the number of total ways of doing something. That's n of s. Remember, that's just the number in the sample space. That's everything. Minus the number of unwanted ways. See, we've seen this before. This a with a apostrophe beside it. It's called a prime, which is the complement, right? This is the complement. So in this case, what we want to do is we want to find, we know that n of s, the total number of ways of arranging anybody on the team, is part A. It's the 40,320. And we don't want the captain and the assistant together. So that's actually what we calculated in part B, because we did figure out how many ways the captain and the assistant could be together. So what we do want in this case is the number of ways they can't be together, which is n of s minus n of a prime, and that's all the rest of them. And that works out to be 30,240 ways. So again, things can start to get complicated quickly if we don't take good care to really stop and make sure we understand the question, to count properly, to take our time, and apply, to really know the different rules, the different counting principles.